Session 1, Docker Introduction. By the end of this lecture, you will learn and you will be able to define what is Docker. Why do we need containers? What all platforms available for Docker? Containers versus virtual machine, Docker architecture, Docker components. That's what you will know. So what is Docker? Docker is a platform. It is a daemon-based application which run in the background. Platform for developers and sysadmins to develop, ship, and run application based on containers. It is open source, created in Go language, and originally on the top of virtualization library of Linux, that was libvirt. We used libvirt in initial days when virtualization just started. I used to deliver training on virtualization specifically. Docker simplifies and standardizes the creation and management of containers. This is the logo, and you see there's a meaning to it. You can see that there's a containers in the ship. So why this icons and why these containers like this? There's a reason for it. If you see containers throughout the world, they have the same dimension, same size, because they are governed by international standards. For Docker also, for this software, we have a lot of standards, standards for storage, standards for networking, standards for security. A lot of standards are working behind it and they're governed by standards. That's why we are using the term standards and also the isolation. Containers create the complete isolation for your application. So why do we need containers? There are a couple of reasons for it. For developers, it enables write once and run anywhere. You just create once and run anywhere. That enables microservices architectures, great for development and testing, for testing of apps and services and production realism. Growing developer community. Second is for operations, portability, and portability, standardization, standardized development, QAs and production environments, abstract differences in operating system distributions and underlying infrastructure, higher compute density, and easily scale up and scale down in response to changing business needs, because this is something very crucial. Nothing is fixed, nothing is rigid, everything is changing. And since business needs are changing, we need to scale up or scale down the requirement. And that is the power which comes with containers. That is for operations. So together it is useful for development and operations, that is DevOps. So this Docker is a great tool for DevOps, whether a developer or operations. Why do we need? What are advantages? The container advantages for developers are it is fast iteration. Means it's very quickly, actually it a few seconds you can create a container, replicate it. Agile delivery, minor changes, you don't have to spin up the entire operating system, only that layer, that component will be added or modified which is changed. So it ensures the agile delivery and immutability, immutable in character, that is immutability. These are advantages for developers. For entire information technology, It has this advantage that it offers cost saving, efficient deployment, and elastic bursting. Think of creating running 4 versions of MySQL database or Oracle database for different requirements, or 4 different set of libraries for testing purpose. In physical environment, you would create 5 physical machines, and then you install each version of library and software on one machine. Even if you are using virtual machines, you will create 4 different virtual machines, and then you will install and deploy the software with different set of libraries in those virtual machines. The containers gives you advantage that you don't need that entire physical machine or virtual machine. Only your application and the required libraries can be created in the containerized environment. So therefore, because of you are not spending on anything on the virtual machine, on the physical machine, they are saving a lot of costs here. And efficient deployment in terms of storage, in terms of speed, in terms of management, a lot of advantages here for efficient deployment also. Elastic bursting, scale up or scale down as you require it. So let's go by the definition of Linux containers now. That was a brief idea that what Docker is, what are the advantages of containers. But what containers are actually? A container is an operating system level virtualization method for running multiple isolated Linux systems or containers on a single host or control host. I was talking about the standardization. This is a container. And because every corner or wall or the door or the size, the dimension, everything is governed by standards, therefore these Linux containers use the same icon, and that's why they are called as containers only. So isolation and standards, these two terms, two words behind the term containers. Why we use the term container for our Docker container or Linux containers? So this is the icon for container. This is the icon for Linux. Generalized icon, not for any brand. It is open source Linux. Let's understand the difference between virtualization and containerization, because this may be misleading sometime that are we talking about virtualization or are we talking about containerization? If I say the virtual machine versus container, what is the difference? I agree that both are based on virtualization technology. So technology behind is virtualization only. But containerization gives you very specific application and the library and the configuration file put into an isolation or isolated container. So let's understand the difference between the two. There's a close resemblance between these two terms. So we need to understand that. So virtualization is like we have a type 1 virtualization where we have the hardware and we install the hypervisor on the top of the hardware. This is also known as virtual machine monitor. And on the top of the virtual machine monitor, we create virtual machines. These are virtual machines. So this is type 1 hypervisor, type 1 virtualization. You can also have type 2, which we are using. You all are using Oracle VM VirtualBox. That is type 2 hypervisor, because you have your laptop, that is hardware. You have your operating system, which is OS X or Windows, and then you are using hypervisor on the top of that, which is Oracle VirtualBox, and then you will be creating virtual machine on it. That is type 2 hypervisor. Together they gives you this environment that you have guest operating system, you have dependencies and application that will make one virtual machine. So it is like a independent villa. This is a house, completely independent house, which is completely yours. There's no interference from anybody. That is a virtual house giving you complete isolation. That is virtualization. Now, if I think the same thing from the containerization perspective, we have the hardware, we have the host operating system, and we install Docker engine. Docker engine means the Docker software, Docker application. And then on that Docker engine, you run your isolated environment, the dependencies and the containers. This is one, this is another, and that gives you container that include your application and your application dependencies. It is like an apartment in a multi-story building. Think of this apartment and see the difference between the two. Though you have independent and isolation here, your house, your apartment will be isolated and will be different, and that will belong to you. But you cannot avoid one fact, you cannot ignore one fact, that all the houses are connected, have some common amenities and common shareable infrastructure among them. And that's the purpose and that's the meaning here. Because all houses are built on the same platform in the same building, there's a common resources to all the houses, still giving you isolation. So the container has that concept which gives you isolation, but multiple containers on a single host machine share resources. That's the different thing. That's the point here. So that's the concept of containerization. In terms of security, virtual machines are more isolated. Containers are less isolated. Look, think of the virtual machine, the villa and an apartment. Size, virtual machines are in gigabytes, means bigger size, and containers are in megabytes, very small in size, because you don't need a complete operating system. Provisioning, virtual machine may take few minutes, but containers take seconds. Operating system wise, virtual machine gives you more flexibility, but containers are less flexible comparatively in terms of operating system. So that's the difference between containerization and virtualization, or virtual machine and containers. The bigger picture. From the operating system perspective, I'm a typical Linux person and I love to get deeper inside. From that perspective, how can I define and explain the containers to you? Very difficult for me, because if any of you is having any background in system programming, you will have one strong point to tell me, hey Ram, what are you talking about? Because in Linux we know only one thing, and that is processes. And these processes are created, destroyed, and managed by system calls. No doubt, no denial of the fact. Every command you use, every process you create is governed and managed by these system calls: fork system call, exec system call, exit, kill, open, close, system, clone. There are so many system calls. Because in Linux, we have very two important points here. One is the two user spaces, the kernel space and the user space. So the user space is where user processes are created. Like user shell, you are working, you make a system call, whether fork or exec, and your regular process will be created. This process will have no interference with the Linux processes. If this process needs to talk to the kernel processes, it needs to make system calls. And that is like this exec system call was made to the kernel, fork was made to the kernel, or any other exit or fork, or all these calls. It can make calls to the kernel. These calls are called system calls. So the regular processes can interact with the kernel by means of system calls, or kernel can interact with the processes by means of system calls. So where is the kernel, where is the container here? And kernel have different namespaces. Namespaces means the logical grouping of resources. These are various namespaces which has two aspects of it. One is the process or the memory, and second is the security context of it. So where is the container here? I don't see anything related to container in this operating system because this is a core architecture of Linux operating system. So I don't see anything here related to kernel when it related to container. Let's try to identify and figure out what is that possible, how containers are created in the kernel. Kernel and containers. Creating containerized Linux processes. What are containers from the operating system perspective? There is no kernel definition. Very clear for what a container is, because in kernel we define only processes. If you have to define it, this is the definition you can say, and this is a system call clone. The clone is the closest definition we have. It creates namespaces for kernel resources, whether it is mount, UTC, IPC, PID, network, user. Essentially it creates a virtualized data structure for you, and that's what how the containerized processes are created. So when you make a clone system call to the kernel, it create containerized data structure for your various kernel resources. So that's the closest definition of containers from the operating system perspective. So an application delivery mechanism with process isolation based on several Linux kernel features. One was the namespace, as I was talking about, which means what a process can see. That includes the process ID, the mount, the network, the UTS, IPC, user, control group. And the control group means what a process can see. That is memory, CPU, BLKIO, CPU account, and CPU set, all these things. We are not going to get inside this part because this is not what we need to learn here. We need to figure out in terms of kernel, how can we define containers, at least have some visual picture of containers running inside the kernel. That this information is sufficient enough to give you a brief idea about what containers actually are and how they are created in the Linux kernel. So how Docker works? Let's talk about working of Docker. Essentially, when you are working with Docker, you are working as a client. This is you. Whether you make a request through the command line or you make request through remote application programming interface. You have a host machine or the computer where your Docker daemon is running. So this is your Docker daemon. Docker daemon is running. This is your host machine where you want to work, where you want to run your container application. And third is important component is the registry where you keep the Docker images, the images based on which you will run the containers. So whether it is Docker Hub or Docker Cloud Registry. So the Docker Hub or Cloud Registry is the place where you keep the images. These are images. So this is the environment. You need three things in order to work with Docker. The client from where you make request to the daemon running on a host through API or through command line. Host where you will run your containerized application. Registry where you will keep your images for your application. So three things involved here. One is the build. First step for running any containerized application is building. You need to build images. To build the images, you make requests from your command line or through the remote API to the daemon process. The request goes to the daemon that I want to build. I want to build the image. So this is building the image. So first step, you supply or you create a Docker file. You send that request to the daemon process, and the daemon will build the image using the Docker file you provide. So that is the first step. You build the Docker images. After Docker image is built, you push it to the registry to safe keep it. so that it can be used whenever you need it. So step number one, you create images by using the daemon through appropriate command. And the command is quite simple, docker build. It will build the image and you push it to the registry so that you can use it or somebody else can use it to whom you give the rights. I mean, whether you want to make your image public or private, that depends on your requirement. Then to run the application or run the containers, you need to pull. The second step, second major work, what you do is you pull the images. You may have not built the images. You may want ready images built by somebody else, maybe official or some other user, maybe private or public. So you need to pull the images from the registry. So you make request from the command line or API to pull the request through the daemon only. So the command will be docker pull. So the command goes to the daemon. Daemon will pull the image from the Docker hub and will put the images into your system. That means that will be the next step. So you will have images on your host machine after pull. So first step, the command goes to the daemon. Daemon pull the images from the registry, and after the image is pulled, the image is in on your system, on your host machine. This is the second phase, second step. What do? You pull the images. Third is run. You run the container based on the images. So to run, you make another call, that you make the call called docker run through the API or the command line, and this call goes to the daemon. Daemon will run the container based on the image which you have pulled or which you have created, and then you will have containers running based on the images. So these are containers. So you are running containers, container 1, 2, 3 containers are running based on different images which you have created or which you have pulled from the registry. This is how Docker works. So we have client, host, and registry. We build the images, we push the images to Docker Hub, we pull the images from Docker Hub or registry, and we run the container based on the images. That's the working of Docker. So the components of Docker from the previous slide is very clear that we need something called Docker image first. This is the basis of a Docker container. It represents a full application. Second is the Docker container. It is the standard unit in which the application service resides and executes. And third is the Docker engine, which is the daemon process, which is used to create, ship, and run Docker containers deployable on a physical machine or virtual machine, or the hosted locally or in a data center or cloud service provider. And registry service is Docker Hub or OCIR, that is Oracle Infrastructure Cloud Registry, or Docker Trusted Registry, cloud or server based storage and distribution service for your images. So Docker images, we need to learn first. What are Docker images? Because the big picture is now clear, what Docker is, how it works inside the kernel. So we need to learn now what is a Docker image. Docker image is a read-only template used to create containers. Remember, it is read-only. Think of ISO. Think of a DVD of an operating system. The DVD have the operating system. You need to install that operating system on a machine, and only then you can run it. It is built by you or any other Docker user, stored in Docker Hub or your local registry. Every image starts from base image. Well, not always. You may have image which starts from scratch. And your image includes application, dependencies, libraries, binaries, configuration file. So we have read-only layers, and unioning of these multiple layers make the Docker image. So technically, by definition, you can say that image is unioned read-only file system. That's a precise definition of image. Then what is a container? It is isolated application platform. Contains everything needed to run your application. There's a typo here. Based on one or more images, launched from Docker image, adds a read write layer on the top of the image. So read only layer, read only layer, read only layer. You add a read write layer, and unioning of these layers, read only layer plus read write layer, becomes the container. So container is unioned read write file system. That's the precise definition of container. Those who know programming, object-oriented programming particularly, it was very easy for them to understand if I say Docker image is a class and Docker container is instance of the class. So think of this example. We have kernel, we have image. Now we add a writable layer to it, it becomes container. So read-only layer, Debian, add Emacs, add Apache, these are all read-only layers. You add a writable layer, becomes container. So this is the container, writable layer, writable layer. So writable layer, when you add on the top of the image, it becomes container. Think of this a real example. This is a container based on Ubuntu 15.04 image. So this is your cryptographic content hashes, the layers, read-only layer I was talking about. So this is a layered file system, the image layer. The moment you add a writable layer, random UUID is added, all writes and deletes go on to this layer, and this is the container layer, that is read-write layer. So that is the difference between image and container for Docker. Docker volume is storage. Storing the data outside the container is mandatory. Volumes are preferred mechanism for persisting data generated by and used by Docker containers. Think of MySQL database or Oracle database or Sybase database, any database. Definitely running application inside the container makes sense to us. But the philosophy that containers are lightweight, that policy will be violated if we say that entire database is stored in the container. Make no sense. The data should be kept outside the volume. Application and libraries, everything should remain in the container. Therefore, we need the storage part to be kept outside the container scope. So we have three options here. One is bind mount. Bind mount means attaching a library path, or sorry, the physical path of the file system to the container. And the container then stores the data in the directory which you mount. That's called bind mount. They are dependent on the directory structure that you specify. Therefore, you tie your container with the physical path on your file system, and so that it stores the data, container stores the data inside this file system path. Problem with this is that you cannot move the container now because this is tied to the operating system. It is glued to the operating system where you are running the container. So that's the drawback. So they're dependent on the directory structure of the host machine. Volumes are completely managed by Docker. That means based on the driver, your volume can be on the same computer or on different computer. Can be NFS server or can be SSH based storage. Can have different kind of drivers possible for that, and that will be external to your host machine as well. In that case, moving the container will become very easy and will have no impact on the storage. Volumes have several advantages over bind mounts. Volumes are easier to backup or migrate than bind mounts. You can manage volumes using Docker CLI commands or Docker API. Volumes work on both Linux and Windows containers. Volumes can be more safely shared among multiple containers. And that's the interesting thing is volume driver let you store volumes on a remote host or cloud providers to encrypt the contents of the volume or to add any other functionality. And lastly, you can have content of the volume pre-populated. I mean, you can already store the data in advance and then make it bind or attach it to the container, and then container will use the data existing. So new volumes can have their content pre-populated by another container. So this is a concept of volumes. So volumes are often better choice than persisting data into containers writable layer, because volume does not increase the size of the container using it, and the volume contents exist outside the life cycle of a given container. So if this is the container, then if you are using bind mount, you are attaching the file system path fix, cannot be changed. You cannot move this container now. If you are using volume, you are managing some area dedicatedly by Docker. That area may be on this computer or another computer based on NFS or SSH. So there are various drivers available. And then we can also have tempfs mount, that is mounting and memory area used within the container, that is a temporary file system mount. These are Docker volumes or the storage for containers. That's all for this session. Recording is available here. The link is working, so you can go and watch the recording. You may find the recording slightly different from what I discussed, but that's good for you. Thank you so much.